Right now, at this exact moment, something is happening in your hand that you have never once thought to question. If you are holding a cup of tea or coffee, the heat is leaving it, moving outward, into your palm, into the air, into the ceramic of the table beneath it. And it is doing this without being asked, without being pushed, without anything pulling the cold air toward it. The warmth is simply departing, patiently, invisibly, in one direction. And it has been doing this since the moment the drink was made, and it will not stop until the cup and the room have reached the same temperature. Not 1 degree of that heat will ever return on its own. Not 1 moment of that transfer will ever reverse. You have watched this happen your entire life. You have never once found it strange. That is the first thing this episode is going to change, because the reason heat moves the way it does, only one way, always the same way, without exception, across every substance and every scale in the observable universe, is one of the most profound discoveries in the history of physics. And it does not involve a force. It does not involve a rule written into the structure of space-time. It involves something far stranger, a kind of arithmetic so overwhelming that it functions as a law of nature without ever being one. It explains why time moves in one direction, why you can remember yesterday but not tomorrow, why eggs refuse to unscramble, why the universe, from its very first moment, has been doing exactly what that cup of tea is doing right now, flowing, spreading, dispersing, and why it will continue until the last cold silence. But here is the question almost no one thinks to ask. If entropy always increases, if disorder always spreads, then the universe today is more disordered than the universe yesterday, which means the universe 1 billion years ago was more ordered than today, which means the universe at its very beginning must have been extraordinarily, almost impossibly ordered. Why? Hold that. We will come back to it. Because the answer changes everything. First, let us destroy something you were almost certainly taught incorrectly. For centuries, scientists believed heat was a substance. They called it caloric, an invisible fluid that poured from hot objects into cold ones. The idea felt completely intuitive. Hot things had more caloric, cold things had less. Heat transferred because the fluid moved from regions of abundance to regions of scarcity. It was elegant. It gave heat a physical identity. It was also completely wrong. Caloric does not exist. Heat is not a substance at all. Heat is motion. Specifically, it is the collective, chaotic, kinetic energy of atoms and molecules. When something is hot, its particles are vibrating and colliding with tremendous speed. When something is cold, those same particles move slowly and weakly. Temperature is simply the average energy of that motion, nothing more, nothing hidden beneath it. This is a simplified explanation to make the idea intuitive. But once that image settles, heat is motion, not substance, a new question rises immediately. If heat is fast particles colliding into slow ones, then every individual collision is governed by electromagnetic forces operating at the microscopic level. And here is the crucial thing. Those forces carry no directional preference. A single particle collision, filmed and played backward, still satisfies every law of physics perfectly. The forces at work are symmetric. So what is producing the asymmetry you see at the large scale? What is making the heat flow one way when the underlying mechanics allow any direction? This is the deepest question in thermodynamics. And the answer is not another force. The macroscopic directionality of heat does not come from a net force operating across trillions of particles. It comes from probability. The collision forces are real, electromagnetic, as always, but no force sums up across all those particles and commands them to move energy in one direction. The one-way flow is a statistical outcome, an inevitability of counting. And the difference between a force and a statistical inevitability is the most important distinction in this entire conversation. Pause. Predict what happens next. Imagine a sealed, perfectly insulated box of air. The left half is hot, the right half is cold. You wait. The particles collide in every direction. The underlying physics permits any configuration. So, will the hot particles ever spontaneously drift back to the left side on their own? Will the two halves ever unmix? Take a moment. The physics allows it. Every individual molecule can move any direction it chooses. So why not? Here is the reveal. They will not. Not because any law explicitly forbids it, not because a force is blocking the path, but because the number of microscopic arrangements that produce a well-mixed state is so incomprehensibly larger than the number that produce two separated halves that random motion will, effectively, never find its way back. We are not talking about a small probability difference. The number of mixed arrangements exceeds the number of separated arrangements by a factor with more zeros than there are atoms in the observable universe. Spontaneous separation is not impossible by decree. It is impossible by arithmetic. The system is not blocked. It is simply overwhelmed by alternatives. This is what entropy actually measures. Not messiness in the aesthetic sense. Not disorder the way a cluttered desk is disordered. Entropy measures the number of microscopic arrangements consistent with a given large-scale appearance. A scrambled egg has an almost infinite number of molecular configurations that all look scrambled. An intact egg has a tiny, precise set that hold the yolk centered, the white surrounding it, the membrane unbroken. When particles explore available states at random, which they always do, they land in the scrambled-looking region essentially every time. Not because scrambling is commanded, because the scrambled region of possibility is almost the entire region of possibility. Notice how your intuition expects a force here. We are trained from childhood to look for pushes and pulls. Gravity pulls, magnets attract, electric fields tug on charges. We instinctively search for a thermal force pulling energy from hot to cold, but no such force exists at that scale. The directionality is produced by counting, by an overwhelming disproportion between probable and improbable configurations. The cup does not cool because heat is being extracted. It cools because the arrangements of atoms consistent with the cup being warm and the room cool are almost non-existent compared to the arrangements where both are lukewarm. Now here is the piece almost every explanation omits, and without it this entire picture is missing its foundation. We have established that entropy increases because disordered states are overwhelmingly more probable than ordered ones. Random motion almost always finds a disordered region. Fine. But this argument quietly assumes something enormous, that the universe started in an ordered state, that there was somewhere lower to be. If the universe had begun at maximum entropy, fully mixed, every temperature the same everywhere, every difference already equalized, nothing would have ever happened. No temperature gradients, no heat flow, no stars condensing from gas clouds, no planets, no biology, no coffee cooling on a table. There would be no arrow of time because there would be no change. So why did the universe begin in a state of such extraordinary, improbable order? This is what physicists call the past hypothesis. The Big Bang produced a universe of almost incomprehensible low entropy, compressed, structured, far from equilibrium. Cosmologists still debate the precise reason. Some believe it is connected to the nature of gravity in the very early universe. Some believe it is a boundary condition we simply have to accept. The debate is unresolved. What is not debated is the implication, the arrow of time, the reason heat moves one way, the reason you remember yesterday and not tomorrow, the reason the universe as a whole is running in a single direction, traces back to that initial improbable state. Entropy has been increasing ever since, not because it must in some metaphysical sense, but because we began in such an unlikely corner of the space of possibilities that outward was the only direction available. Every cup that cools, every candle that burns, every star that exhausts its fuel is the universe spending the inheritance of order it was given at its beginning. Now let us go one level deeper to where quantum mechanics meets this picture. This is the part that most popular explanations skip entirely, perhaps because it is harder to visualize, but it is where the picture becomes complete. At the quantum scale, particles do not have definite properties the way everyday objects do. They exist in superpositions, spread across multiple possible states simultaneously. When a quantum particle interacts with its environment, another particle, a detector, a stray photon, its possible states become entangled with the states of whatever it interacted with. The information about the original configuration spreads outward, tangling with more and more of the surrounding world, becoming practically inaccessible as it disperses into a vast web of correlations. This process is called decoherence, and it is itself a form of entropy increase. Not the same thing as entropy, but driven by the same logic. The space of entangled, spread-out states is vastly larger than the space of clean, localized, coherent ones. A quantum system interacting with its environment almost always moves toward greater entanglement, greater spread, greater loss of accessible information, for exactly the same reason that gas expands to fill a container. The outward direction is not commanded. It is simply where almost all the room is. So the arrow of entropy runs not just through the classical world of colliding billiard balls. It runs through the quantum foundation beneath that world, through every measurement, every interaction, every moment of contact between a quantum system and its surroundings. The one-way direction is baked into the structure of possibility itself at every scale. You have probably felt this without fully naming it, that sense that time only runs forward, that you remember yesterday but not tomorrow, that broken glass does not return to wholeness, that you grow older, never younger. We tend to blame time itself for this. We say time has an arrow, a direction built into its nature. But consider what we have just established. Every fundamental equation in physics, Newton's laws, Maxwell's equations, quantum mechanics, even general relativity is time-symmetric. Run them backward and they still hold. A planet orbiting the sun in reverse is a valid solution. A photon traveling from detector back to source is mathematically legal. The laws of physics carry no preference for which way time points. The only law that prefers a direction is the second law of thermodynamics. This has led some physicists to propose that time's arrow is not fundamental to time itself, but is instead a consequence of entropy's arrow. That we experience time as flowing forward, because AUP is increasing, and increasing entropy is what makes the future different from the past. When things change, we call that the passage of time. When entropy increases, things change in one direction. Therefore, time, as we experience it, may be entropy wearing a different name. But here it is important to be precise, because this is an active debate and not a settled conclusion. The thermodynamic arrow, the direction of entropy increase in physical systems, and the psychological arrow, the felt, lived experience of time passing, are related but distinct. You can have entropy increasing without a conscious mind to experience it. And the relationship between physical time asymmetry and the subjective feeling of being embedded in a forward-moving present is a question that touches philosophy and neuroscience as much as physics. Feynman himself was careful on this point. He understood entropy with great clarity. He was more cautious about claiming that thermodynamics alone explains everything we mean by time. What is not in dispute? In a universe at perfect thermal equilibrium, where every temperature difference had vanished and entropy had reached its ceiling, nothing would change. And in a universe where nothing changes, the distinction between before and after becomes practically meaningless, not because time as a mathematical coordinate disappears, but because nothing would mark the difference between one moment and the next. The concept loses its grip when entropy stops moving. Pause again. Predict this one. I show you two video clips of gas in a sealed container. In the first, gas spreads from one corner until it fills the entire box. In the second, all the gas spontaneously rushes back into that one corner. Which video is real? You would know instantly, without training, without equations, because your mind is, without realizing it, tracking entropy. Your intuitive sense of before and after, the most basic feature of your experience of being alive, is your nervous system doing thermodynamics. Every time you perceive time passing, you are perceiving the universe moving from lower entropy to higher entropy. You are feeling the past hypothesis unfold. That sense of forward motion that feels so personal, so interior, so uniquely human. It is, at its root, the universe exhausting its inheritance of order. Now consider life. A living cell is a remarkable local exception to the spread of disorder. Your body maintains extraordinary internal organization. Proteins folded into precise shapes, DNA storing information in specific sequences, cells holding their interiors sharply distinct from everything outside. If entropy always increases, how does organized life persist? The answer is that life is not violating the second law. It is using the precise loophole the second law permits. Life maintains local order by consuming an external source of low entropy. Plants absorb sunlight, concentrated, highly ordered energy arriving from a star that is itself burning through the low entropy fuel produced in the Big Bang. That energy is used to build organized structures. Animals consume those structures. The total entropy of the entire system, organism, sun, environment, still increases. Life is a local eddy of order in a river flowing toward disorder. The cell that maintains its precise organization does so by accelerating the spread of disorder somewhere else, in exactly the way the second law demands. You are not an exception to entropy. You are one of the more elaborate routes the universe has found toward higher entropy. The egg that refuses to unscramble exists because a star has been scrambling itself for 5 billion years to pay for it. Consider the muon, a particle born when cosmic rays strike the upper atmosphere, roughly 60 kilometers above your head. Muons are unstable. They decay in about 2 microseconds. At their speed, they should not survive the journey to the ground. But they do, because at near-light speed, relativistic time dilation causes their internal decay clock to run slowly relative to an observer at rest. This is a consequence of special relativity, of the geometry of space-time, not of entropy directly. But the lesson it carries is consistent with everything we have been building. The universe operates under deep structural constraints that make certain outcomes possible and others effectively unavailable. Relativity constrains time, thermodynamics constrains direction. Both are limits, not forces, not commands, but the shape of the space in which reality is allowed to exist. Your GPS demonstrates this in the most concrete engineering terms possible. Satellites orbit at speed and at altitude. Both factors alter clock rates. Time dilation from velocity, gravitational potential difference from altitude.